Welcome to the next topic on the principles of operating systems. I am Dr. Emmanuel Doyle. Today we'll be looking at the lecture 3 in this series and it's titled CPU scheduling. We'll be looking at basic concepts, scheduling objectives, levels of scheduling, scheduling criteria, scheduling algorithms. We'll look at different types of scheduling algorithms like first come, first serve, shortest job first, and others. We look at multiprocessor scheduling, real-time scheduling, and algorithm evaluation. Now, the basic concept of a computer system is that you first of all have to load data. You have to store it from file. Now, this is what we call CPU operations or CPU bus. Now, within the CPU bus, there is an execution of a process from the where it loads, it adds, it reads from files, and is happening. CPU is making certain decisions based on the program that was written. Now we also have the I/O burst cycle, and this is usually when it is waiting for an I/O. The system is waiting for an I/O. All right. Then we have something like a so we have the cycle going on between CPU I/O gradually until we get what we need, until we get our process running completely. Now, we get maximum CPU utilization when we use multi-programming. From previous lecture, we had seen that it's better for multi-programming instead of single programming because we can schedule more jobs while when one process is running the wait cycle when it's doing I/O bursts, I/O wasting time doing I/O work. Another process can be using the CPU at the same time. So the CPU I/O burst cycle, this is it. Process execution consists of a cycle of CPU execution and I/O wait. So you have your burst, I/O wait, CPU burst, I/O wait. And gradually you get the system running. Now, this is an example of the CPU distribution. Now, from this CPU bus distribution, it's been seen that we have more concentration of burst between the 0 and the 8 milliseconds. So between here, you have as high as 140 or 160, you have up to 150 system processes here tend to be very high that around the maybe 4 milliseconds mark. So more processes do more of short CPU burst times. So before you have CPUs, fewer ones go from higher than 8 to 16 to 24. Very few. Most are just within this burst time. Now, scheduling objectives, one is to enforce fairness in allocating resources to priorities. We want to make sure that every process gets appropriate execution. We don't want the CPU to just sit down working on only one program. It should be able to work on each program fairly. Give a process its due time, and then after that, give another process. Now we have to enforce priorities. Some processes are more important than others or have higher priority than others. So if any process has a higher priority, then that process definitely has to be given privilege to execute. And that privilege can only be enforced by using the scheduling system. Another reason why we use schedules is to make best use of available system resources. Like I've said, the system resources are it's not good for you to them just be idle when there is a process that needs to work. The CPU cannot be idle when we have other processes that are supposed to be executed. So we need to give it to the CPU as R&D. The next one will be give preference to processes holding key resources. Give preference to processes that are holding key resources. we want them to execute quickly and release those resources for others to use. So it's necessary to do that. Give preference to resources, to processes exhibiting good behavior. So if a resource, we have seen that a resource, there are certain things that make good behavior, and we'll see it later in the course. But if a process is not spending so much time trashing, might be spending so much time doing I/O work, you give it available CPU when it needs it and you work with it. Then also, it helps to degrade gracefully under heavy loads. Because if you give a process that has heavy, maybe we have lots of processes running, there are so many, then scheduling can help to make sure that the system degrades gracefully by shutting down some processes that may have been of lower priorities and doing the one with higher priority gradually until it gets itself back. Now, let's look at the program behavior issues. Now, a program based on what device it really needs can be I/O bound or it can be CPU bound. Now, if we see a process that is I/O bound, it has a short burst of CPU. That means it spends a short time in CPU before blocking for I/O. Spend more time doing I/O work. So when doing that, it goes more time doing waiting for I/O input-output activities. It could be waiting for something from the keyboard. It could be waiting to print. Now, or could be waiting to put something display on the monitor, on the screen. A CPU-bound process has extensive use of CPU before blocking for I/O. It spends more time doing CPU work. It needs the microprocessor for longer periods. Now, for urgency and priorities, we need to, this is another behavior of a program. It could have a high priority and needs to execute it fast. For example, maybe a monitor needs to be on while we are doing some work, and then suddenly it has to come on, then it becomes of higher priority compared to other processes. You could just touch your mouse and see a screen that has been down and it needs to come up. You need to give it a priority. And we also have frequency of preemption. Preemption means that we can stop a process while it's executing. So if a process is executing, how many times can we stop it? That's what we mean by frequency of preemption. How many times can you stop it and maybe run the process all over again? So we have to know that, be able to allow a program to be able, it can be preempted, good. If you cannot, then you have to run its course. Then we also have the process execution time. Execution time is the time that every process has to run. That's the time allocated to it. Like I said, a process can have a burst time of 1 second, 8 seconds, 5 seconds, milliseconds. And these milliseconds need to be properly executed in time. Now, another issue that needs to be looked at is time sharing. That's the amount of execution time process has already received. Time sharing. Now, in time sharing, we want to share the time for each process in an organized manner based on the scheduling algorithm we are using. We share time, but we don't want one process to just use up the whole time, else there could be problems in our system. So we have to share time fairly. So sharing time fairly. So time sharing is the amount of execution time process has already received. Now let's look at the levels of scheduling. Right. Here is the process where we use to get a job running. In this diagram, we have jobs waiting to enter. And when the job enters, the job is waiting for initiation. Now, while it is waiting for initiation, we see it as high-level scheduling. High-level scheduling. When the process is waiting for activation, then we now activate that process. That means it starts executing here. Within this period, it has an intermediate level scheduling because it's already been doing some work. Then we can wait for activation again, come back again, be executed until it is through. Then you can dispatch that process if it's through, becomes a running process, or we go and queue it again for it when its time is out to come back again and be executed. So within this period, we have a low level scheduling here. And then when the job is completed, we have complete jobs go out. So high level scheduling or job scheduling selects jobs allowed to compete for CPU and other system resources. It selects jobs from the pool, job pool, for it to use CPU. At the intermediate level or medium-term scheduling, we select jobs which to temporarily suspend to smoothing fluctuations in system. So at that level, systems are already running. So you know that they are already started being executed. So they have one level scheduling at that level. Now, at low level scheduling or dispatching, we select the ready processes that will be assigned the CPU. Ready queue contains PCBs or processes. That's just what it is. Low level scheduling or dispatching selects the ready process that will be assigned to the CPU. Now let's look at the CPU scheduler, which is look at the short-term scheduler here. This selects from among the processes in memory that are ready to execute and allocate the CPU to one of them. Now, there's a difference between the dispatch we saw at this level and the CPU scheduler. Now, here, when we talk of at this level, the job scheduler, it picks jobs from the job pool, which could be in your hard drive, or it could be in your RAM. It picks the job here and puts it in the ready queue. Picks the jobs, places them in the ready queue. So that is work of the job scheduler, which we sometimes call the long-term scheduler. But the CPU scheduler or short-term scheduler selects among the processes in memory that are ready to be executed and allocates the CPU to one of them. We have non-preemptive scheduling. Non-preemptive scheduling are scheduling where you don't stop the process once it starts. Once CPU says the process keeps the CPU until the process exits or the process switches to a waiting state. Those are the only things that happens in preemptive scheduling. But in non-preemptive scheduling, now in preemptive scheduling, processes can be interrupted and must release the CPU. So you need to coordinate access to shared data. So that's the difference between preemptive and non-preemptive scheduling. Now let's look at CPU scheduling decisions. CPU scheduling decisions may take place when a process switches from running state to waiting state, or it switches from running state to ready state, or it switches from waiting to ready, or switches or terminates. Now, in the previous lecture, we had seen the different states where the process can be in. Now, so CPU makes decisions when it needs to switch from running state to waiting state. When it was executing, running state when it was executing, and waiting state is when it needs to wait for maybe I/O work, or it needs to wait to get data from any other I/O device. Scheduling under 1 and 2 is non-preemptive. 1 and 4 is non-preemptive. If you schedule switches from running state to waiting state, it's non-preemptive. Just does it. Once it completes, it switches from running state because it needs I/O work to switches. But when it ends also, it's non-preemptive, it just terminates. But from running to ready state and from waiting to ready state, those are preemptive. That means we can interfere with them. Now remember this CPU scheduling diagram. We said that the process that can be in different states. For example, it's in the start state. That's when it is admitted. From start state, it will then be admitted into the ready queue. When it's in ready queue, it now becomes ready state to be executed. And then when you get the CPU, it's now in running state. And once it starts running, If it does not complete what it needs to do, it now goes into waiting state. And we say that that is because an IO or an event needs to occur. So it goes to waiting state. When it's completed, it goes back into waiting state and gets executed again. Now, the scheduler dispatch handles from moving it here. Scheduler dispatches it from ready queue to running state. From ready queue to running state. And for it to run means there's the scheduler moves it from here to here. The short-term scheduler that moves it, allocates it to the CPU when it's running. Now, once it finishes, it exits and is terminated. But if it's running and there's an interrupt, it can head back into the ready queue. Interrupt could be maybe time slot allocated to it has expired. It now goes back and lines up again. Basically again. That's what happens there. Now let's look at the dispatcher. The operating system dispatcher module gives control of the CPU to the process selected by the short-term scheduler. The dispatcher module gives control of the CPU to the process selected by the short-term scheduler. This involves switching context, switching to user mode, jumping to the proper location in the user program to restart or continue that program. So the OS dispatcher module gives control of CPU process selected by short-term scheduler. Now, if we talk about switching context, that is where it automatically saves the previous process it was working on and loads a new process. And that new process will now switch into being executed from ready mode to running mode. So the operating system dispatcher module gives control of the CPU to the process selected at short-term period. Now, let's look at dispatch latency. Dispatch latency is the time it takes for the dispatcher to stop one process and start another running process. The dispatcher must be very fast. Now, that is the dispatcher, the speed for it to switch from one program to another is called dispatch latency. Let's look at some of the criteria that we really look at when we are running. One of them is scheduling criteria. CPU utilization. CPU utilization keeps the CPU and other resources as busy as possible. So the CPU utilization is usually how many processes was executed by the CPU within a certain time unit. Because the aim is to keep the CPU and other resources as busy as possible. So you are looking at how many processes were executed within a certain time unit. All right, so you want it to be high. It's usually calculated, look at it in percentages. Now look at throughput. It's the number of processes that complete the execution per time unit. Throughput, number of processes that complete the execution per time unit. So if you have maybe 5 processes run in 30 milliseconds, you can do that. That is throughput. From 5 processes run for that. And if we are looking at the CPU utilization, we want to know the percentage period. Maybe 30%, maybe a CPU was for 40%. That is how long we kept for 80% of the time it was running. That's how busy it would be. We aim to have it as much as 30 at 100%, and most times we try to achieve 100%. And this one shows how many processes were executed within time. Let's say the time could be 30 minutes, seconds. All right. Now, turnaround time is the amount of time to execute a particular process from its entry time. It's the amount of time to execute a particular process from its entry time. So, turnaround time. How long did it take a process to enter from the moment it arrived in ready queue to the moment it was fully executed? That is what we talk about turnaround time. How long did it take it to be fully executed? Right? We also talk about waiting time. Waiting time is the amount of time a process has been waiting in the ready queue. How long did it wait in the ready queue? It's always important because if it waits so long, it may never be executed, or so we try to reduce waiting time. Response time in a time-sharing environment. That's where we barely use response time. Amount of time it takes from when a request was submitted until the first response is produced. The first response is produced. Remember, note it is not the output. At the time the first response was picked, that is when we talk about the response time. So we need to have response time as fast as possible in a time-sharing environment, especially. So for optimization of any scheduling algorithm, to optimize the overall system, we need to have the maximum CPU utilization, and we need to have the maximum throughput. That means we want the CPU to run as much as 100%, and we want many more processes running within that time. Much processes being executed within a unit time that is available. To optimize individual processes performance by having a minimum turnaround time, minimum waiting time, and minimum response time. We don't want processes to keep on waiting. So waiting time should be minimum, response should be picked immediately, and it should finish early. Now, let's look at some of the scheduling algorithms. One of them is first come, first serve scheduling, also called sometimes FCFS. Now, in this policy, a process that requires the CPU first is allocated the CPU. That is it. So once you arrive in a queue, the process that requires the CPU first is allocated the CPU first. It is a non-preemptive scheduling algorithm because you cannot stop it. Once it starts, it has to run to the end. Now, this is usually implemented using first in, first out queues, FIFO queues. Here, an incoming process is added to the tail of the queue, and a process selected for execution is taken from the head of the queue. So you have a process. Let's have a diagram of a process of a. So we have. Let me get a pen. Now we have our FIFO queue like this. Have the different processes I'll put like this. So let me say this is process A. Then we have a process B. So process A is first picked by the CPU before process B and process C. How it's done, right? That's how it's done. Now, the performance metrics here is that average waiting time is average waiting time in queue. We calculate the average waiting time in the queue here. Then the Gantt charts are used to visualize the schedules. So we are going to try and see how Gantt charts are being used to visualize first come, first serve. Now here, the first come, first serve schedule you can see here. This is our, let me get my highlighter back, my laser pointer. Now this is the table. Now process here where you have process 1, 2, and process 3. Each having their different burst time. Process 1 has 24, process 2 has 3, and process 3 has 3 milliseconds. Now, suppose the arrival time for the process is P1, P2, P3, and the arrival time at the same time. 1, 2, 3 just arrived before the CPU was free to start picking. Now, you will see there, this is the Gantt chart that is being used to visualize the setting. This is the Gantt chart. Now, the Gantt chart says pick process 1 and run it for the entire 24 seconds. Before you pick process 2, run it for 3 seconds, and then pick process 3 and run it for 3 seconds. You can see that. So we have to complete each process first before you pick the next one. So you can see a waiting time. P1 never had to wait because the moment it arrived, the CPU picked it immediately and was executed. There was no wait. So it had 0 milliseconds. Process 2 had to wait for 24 milliseconds up to here before it was picked. So it waited for 24 milliseconds, while process 3 had to wait for 27 milliseconds before it was picked. So with that calculation, you can have an average waiting time of 0 plus 24 plus 27 divided by 3, and that gives us 17. So our average waiting time using first come, first serve for this set of processes is 17 milliseconds. Now, suppose the arrival time was changed. The arrival order was changed for the processes. We had P2 arriving before P3 and we had P1 last. You can now see it now operates using the Gantt chart. We now had a different arrangement. P2 automatically was executed immediately, so it ran for 3 seconds from 0 P3 started at 3 milliseconds, while P1 started at 6 milliseconds. We now find out that here, P1 waited for only 6 milliseconds, P2 waited for 0 seconds, and P3 waited for 3 milliseconds. So the average waiting time was 6 plus 0 plus 3 divided by 3 gives 3 milliseconds. Now, 3 is much better, right? 3 is much better. You can see. Now, you starting with the shorter one tends to give us better performance than starting with the long one. But the problem here is the convoy effect. Short processes behind long processes, like one CPU bound process and many IO bound processes. So you can have a convoy effect here where you have all the short processes must finish first before the long process. All right, they are all lined up. So that's one of the things that had to be looked at in first come first serve. Now let's look at shortest job first. Shortest job first scheduling is associated with each process. The length of its next CPU burst time. Use this length to schedule the process with the shortest time. All right. So here we are looking for a process that has the shortest time, the shortest burst time. So the shorter you are, the higher your priority. You'll be taken first before the next one. So you use this length to schedule the process with the shortest time. There are two schemes. One of the schemes is non-preemptive. Once the CPU is given to the process, it cannot be preempted until it completes its CPU burst. You must complete being fully executed once you add. And that is very similar to what we just did with let's confess that when we turned them around from using the longer burst time first before we using the shorter burst time. He said we were using the shorter burst time before the first one. We noticed it performed better. So that's why this algorithm now came out. The second one is preemptive. If a new CPU process arrives with CPU burst length less than the remaining time of the current executing process, preempt. Also called shortest remaining time first. So it's also called shortest remaining time first. We'll look at it also. So we have shortest job first, the non-preemptive and the preemptive. Shortest job first is optimal. It gives minimum average time for a given set of processes. The non-preemptive shortest job first scheduling, let's look at it. Here you have a process, example 3, process P1 arrived at time 0 with a burst time of 7, process P2 arrived at time 2 with a burst of 4, process 3 has arrival time at 4 seconds with a burst of 1, and P4 had an arrival time of 5 milliseconds in all with a burst time of 4. Now please note most of this time are in milliseconds. So in case I mix up seconds and milliseconds, I actually meant milliseconds. Now the Gantt chart for schedule is seen here. We are looking at non-preemptive shortest. When process 1 arrived at time 0, it started to be executed immediately. Now note, while process 1 was running, process 2 arrived at 2 seconds, 3 arrived at 4 seconds, and 4 arrived at 5 seconds. So they were already in the queue while process was running. But process 4 ran completely till it finished processing at 7 seconds. Now after 7 seconds, the CPU now looked through the table and noticed that process 3 was shorter with only 1 second. So it picked process 3 and ran it for 1 second up to 8 seconds. Now it looked again and noticed that process 2 had arrived. Process 5 also was 4, but process 2 had arrived before process 5. So here you will now choose who arrived first. So you now pick process 2, completed it before picking process 4 to complete its 4 milliseconds. So in the process, we now have the process in order of P1, P3, P2, and then P4. So let's look at the waiting time. Waiting time can be calculated as response time minus arrival time. Response time minus arrival time here. So if we look at it here, P1 is equal to 0. They did spend time for response. So 0, arrival time was 0. So it just started immediately. So it had 0 milliseconds of wait. P2 now, was picked at 8 milliseconds. That was the response time. It arrived at time P2, 2. So 8 minus 2 gives us 6 milliseconds. P3 also was picked up at 7 milliseconds as the response time minus the arrival time, which was only 2 milliseconds, 4 milliseconds rather. So we had a total of 3 milliseconds. P4 was picked up at 12 milliseconds and reduced it by the arrival time, which is 5 milliseconds. So 12 minus 5 gives us 7 milliseconds. So the average waiting time is equal to 0 plus 6 plus 3 plus 7 divided by 4, which is equal to 4 milliseconds. So the average waiting time is 4 milliseconds, whereas this same job, when we did it using first come first serve, we had kind of different. If we do it with first come first serve, we will have a different value. But for now, let's move on. We are going to do a calculation using just one set of tables to the end with the different algorithms, and then we'll see the differences. Now, look at the preemptive shortest job first scheduling, also called shortest remaining time to finish, SRTF, shortest remaining time to finish. In this one, we have process P1, and you see they have the same time of 0245 and the 74, first time of 7414, the same thing. But here, all right, they're able to stop the process from running. So here I have the Gantt chart schedule. P1 arrived at time 0 and was picked up immediately, and it ran for 2 seconds. And while it was running, P2 arrived, and P2 was 4 seconds. All right, but remember P1 was 7 seconds, so it ran only 2 seconds, which means it had 5 seconds left. P2 had 4 seconds, so it had to dump P1, which had a set of 5 seconds, and go and pick P2. P2 ran for 2 seconds, and while it was running, P3 arrived, and P3 is only 1 second. So P2 had to pause to give priority to the one with only 1 second and let it run. So he allowed P4 to run, P3 to run, and then exit. Then by the time it ran the 1 second, it exited, P4 arrived, and P4 was 4 seconds. So here we have P2 remaining 2 seconds, it ran the 2 seconds, then pick P4, which was 4 seconds, and ran it complete to 11 seconds. Then now pick P1 that was remaining 5 seconds and ran it to the end. So you now see how the time went. So the response time, the waiting time, we do it the same way. P1 is equal to, the first time it arrived, we had no wait, to 0 minus 0, we have 0, plus the second time at 11, where it had to be picked up again, minus the 2 seconds that is spent here. So we have 11 minus 2, which is equal to 9. P2 arrived at time 2 and was picked up immediately. So we have 2 minus 2, which gives us 0, plus 5 minus 4. And 5 minus 4 gives us 1. So it had only 1 wait time. P3 arrived at time 4 and was picked up immediately. P4 arrived at P3 arrived at 4 seconds and was picked up immediately. So it had a waiting time of only 0. Then we have P4 arrived at time 7 and was picked up when it arrived at 7 seconds. All right. Remember, P4 arrived at here. It arrived at 5 seconds. It was picked up at 7 seconds. So we have 7 minus 5, which gives us 2. So because of that, the average waiting time is equal to 9 plus 1 plus 0 plus 2 divided by 4, which gives us 3. So we have an average waiting time of 3 seconds only. Now, the question now is, how do we determine the length of next burst? Remember that the burst time is more or less an estimation. The system does not really know how long the process will take to execute. So it has to do some calculation. So one can only estimate the length of burst. Halting problem cannot in general determine if a program will run forever on some input or complete in finite time. That's a problem, well, problem when you cannot estimate the actual burst, because you could pick a program and don't really know how long it will run. It could be a big process and say, okay, you have a guesswork and it keeps on running and follow-up programs will never stop. So that's why we had the issue of during CPU, when you are guessing burst time or estimating burst time, there's that issue of a halting problem. When do we stop? How do we stop? How are we sure we're even going to stop? So you estimate the next CPU burst by an exponentially weighted moving average. Exponentially weighted moving average over previous ones. All right. It's like saying the CPU looks at previous programs and based on how long they took, it can estimate that, okay, the next one may take the same time or more time. All right. So it weighs it based on what it had seen earlier. So it noticed that, okay, the other one spent 4 seconds, the next one could likewise do the same. So it estimates the next CPU burst by an exponentially weighted moving average over previous ones. So we have T of n is equal to the actual length of burst time. T of n plus 1 is where we have the predicted value for the next CPU burst. How far is the weight? We're looking at between 0 and 1. And we can now define that predicted value for the next burst is equal to alpha, which is the weight, times the T of n, which is the actual length of burst time, plus 1 minus alpha times tau of n. Now, this value is calculated to predict the value for the next burst time. So with that prediction, you can have a value within this period. So if you have a burst 6, the guess will give you 10. If you had a burst of 4, the guess will give you 8. You have 6, it gives you 6. You have a burst of 4, you can get 6, 13, 5, 13, 9, and 13, 1. Now let's look at the round robin scheduling algorithm. This one has a fixed quantum time, which each process must run before another process is being picked. So here, each process gets a small unit of CPU time. Time quantum usually between 10 to 100 milliseconds. After this time has elapsed, the process is preempted, moved to the end of the ready queue, and the process at the head of the ready queue is allocated the CPU. So here, the n processes each process has a time quantum equal to q. So all processes have equal time. Each process gets 1 over n CPU time in chunks of at most q at a time. No process waits more than n minus 1 times q time units. Performance consideration. Now, the time slice q, if it's too large, we have a FIFO behavior. For example, if you have a process that is only 10 seconds and you have a 20-second quantum time, and then you have maybe 3 processes that are just 10, 5, and 8. Now the Q quantum time is 20. So it makes no difference because all of them will still go as they come. So it's now first in, first out. As you arrive, you use your entire time and move on because none is up to or greater than 20. Then if the time slice is also too small, you have an overhead of context switch, which means you'll be changing context switch too often. You'll be changing from one process to another so often, and that is an expensive overhead because the system is wasting so much time doing switching from one process to another. So what we are looking at, need to have 70 to 80% of jobs blocked within time slice. 80 to of 40% blocked within time slice. That means we are looking at picking a time slice that will ensure that at least 80% of the jobs are done, all right, in a faster way. So we could pick our time slice to be within 70 to 80% of the jobs, greater than 70 to 80% of the job. Since we know that we are having short time slices, so if we can pick a shorter time slice, the better. Let's look at this example of a time slice here. We have processes 1, 2, 3, 4. P1 has 53, P2 has 17, P3 has 68, and P4 has 24. Now, this is the Gantt chart. Now, in the Gantt chart, we can now see we are giving a quantum here. And the quantum is on average time of 20. P1 was given 20 seconds, all right? Now, so P1 was taken, it ran for 20 seconds, stopped. Pick 2, P2, since it's 17, it ended at 37. You now pick P3 and it ran for another 20 seconds to 57. P4 now ran for 20 seconds to 57. So 1, 2, 3, 4 have finished. Now pick P1 again, run it for another 20 seconds to 97, finish. P3, run it for another 20 seconds to 117. Then set it again back to ready queue. Pick P4, run it again to 121. And P4 is gone because P1 had only 4 seconds remaining, so it's gone. It goes out here. Now pick P1, run it for another 20 seconds, but this was the last time, so it was less than 20 seconds before you now move to P3, run for 20 seconds, and do the last one. So with that, you can now see that there are two ways we can calculate the waiting time for Gantt chart. One, you can use each of the waiting time and add them together. So waiting time by adding the wait times. If you look at this process, we now have P1, when they arrived, it waited for no seconds, so it started immediately 0. Then you now waited for 20 seconds, so we had 77, which was the next time was pick minus 20. So P1 ran from 0 to 20, it stopped. It was picked again at 27. Remember, they'd already done 20 seconds, so and remove that 20 seconds from it. Then the next time it happened again, we had 121 minus 97, which was when P1 was picked again. So we now had 0 plus 57 for 24, and that gives us 81 at the time it waited. P2 was 20, immediately arrived, it's picked at 20, it waited for only 20 seconds, and then worked for 7 seconds, and then it waited only 20 milliseconds. P3 arrived at time 0, but was picked at P3 at 37. So 37 minus 0 gives us 37. Then it was picked again at 97, and then minus 57 here. And then we had 134 minus 117 here. We arrived here. It went again 154 minus 154, because when it arrived here, right, 134 minus 137, when it came here, it ran here and it ran again. So there was no delay here, any 0. So 37 plus 40 plus 17 plus 0, 94. Then the next one was P4. P4 had 57, was picked up here. 57 minus 0 when it first arrived. Then it now went and was picked up at 117 minus 77. That's when it arrives here. So we have 57 plus 40, which gives us 97. Yeah, add up all these, 81 plus 40 plus 94 plus 97 divided by 4. We have 292 divided by 4, which gives us 33 milliseconds. So typically, we had round robin gives a higher average turnaround time than shortest remaining time first, but better, has a higher turnaround time, but it has a better response time because everybody speaks faster, but usually has longer turnaround time before a person will feel finished. It takes some more time. Now, another way we can look at it, we can use another technique, which is waiting time is completion time minus burst time. That's the faster way of looking at it. Now, we pick up our chart. We have the same diagram here. Now, we look at processes. Process 1 complete at 134, process 2 complete at 37, right? 37, 134. P3 finish at 162, and then P4 will finish at 121. So we tabulate them here. Now, for us to get the answer, remember that the burst time is 53. Now, burst time is the amount of time it is supposed to be executed. But this is completion time. So if we go by this, we now say The amount of time when it completed was 134 times, but how many times did he use out of that 134 times? We have 53. So that gives us 81. Same thing, P2 had a completion time of 37, but it used only 17 of, so it had a waiting time of 20. Likewise, P3 was completed at 162, but it had a waiting time of 68, and that gives us minus 68 gives us 94. P4 has 121 minus 24, which was the burst time, and gives us 97. So with that, we still have the same 73 milliseconds as the waiting time. Now let's look at priority scheduling. Now, priority scheduling is a process that is executed based on the priority. How important is it, or how we have prioritized it, the system has prioritized it. So a priority value or integer is associated with each process. This priority can be based on the cost to user, the importance to the user, the aging, or the CPU time used in the last 6 hours. So let's explain each. Now, cost to user could mean that if this system should delay, something not so good may happen. So a user may say, okay, if, for example, your monitor turns off and it's not refreshed, then you don't see what's actually happening. So it could be said, oh, right, that is a more valuable process. So let it happen. Importance to user, the same thing. Then aging, if a process has stayed so long and it has not had CPU time, then we can make it to have a higher priority. It can be increasing its priority until it gets fast process time. Then percentage CPU time is used in the last 6 hours. If a process has spent so much time and it has not used CPU time much, we can increase its priority. But the one that spent so much time, we can reduce it so that everywhere will be more balanced. So CPU is allocated to processes with the highest priority. There are two types of priority scheduling. We can have preemptive and we can have non-preemptive. All right. So priority scheduling can be done, and preemptive means it can be stopped. Non-preemptive means that once it starts, it has to finish. So we have already seen examples of the priority scheduling. One is the shortest job first, which has a priority scheme where the priority is a predicted next CPU burst time. Remember that shortest job first, we are looking at the shorter priority. The shorter burst time has higher priority. So higher priority number is equal to lower priority. For example, 0 is higher than priority 1. Now, but the problem that priority helps to solve is starvation. Low priority process may never execute. So if you have a process between 0 and that process is 4, process 0, 1, 2, 3 keep on not being executed and 4 will never be. So the solution is to add a counter that handles aging. As time progresses, increase the priority of the process. So a process that is waiting for longer time, maybe after 10 microseconds, you increase its priority from 4 to 3. Again, after 10 microseconds, you increase again to 2. So you keep on increasing its priority until it has a privilege of being executed. Now, let's look at priority scheduling here. And we're assuming that low number to be higher priority. So we have process here from P1 has burst time of 10, but priority of 3, P2 1, priority of 1, P3 2, a priority of 4, P4 1, priority of 5, P5, and then priority of 2. Now in this kind of situation, now when we are running, we start immediately with priority 1. Priority, the highest priority is 1. Priority 1 is executed first, P2, and then priority 5 comes next because it has a 2 priority. It runs for its own 5 milliseconds. In priority 3, which is P1, runs for 10 milliseconds before priority 4, which is P3, comes here for 2 milliseconds, and then finally priority 4 comes to finish up with 1 second. Even though it had a shorter time, but it had a last priority because it's based on priority and not on. So the waiting time in this situation now gives us 6 plus 0 plus 16 plus 18 plus 1 average wait. We are going to look at another algorithm called multi-level queue. Now, in multi-level queue algorithm for scheduling, the ready queue is partitioned into separate queues. For example, you can have a queue that handles system processes. You can have a queue that handles the foreground processes. That one could be interactive. Then you have the one that handles background processes, which are batch processes. And then you have maybe one with lower priority that can handle student grades. Now, all of them could be working, each queue could be having its own scheduling algorithm differently. For example, the foreground could be working using round robin and the background could be working using first come, first serve. All processes are assigned to one queue permanently, so it never changes. Scheduling must be done between the queues. One queue must finish all the processes within its queue before it moves to the next queue. That's how the scheduling works. Now, there are different algorithms that can be used on multi-level queues. For example, we could use fixed priority. Now, in fixed priority, it serves all from the foreground before serving those in the background. Now, this is an example. In fixed priority, you could say that let the foreground have all the priority 1 before the background having priority 2. And automatically, it has to finish priority 1, which is the foreground, before it now goes on to priority 2, which is the background. And this creates a problem which can be a possibility of starvation. Then another way is looking at it is using time slice. Now in time slice, each queue gets some CPU time that it schedules. For example, we can say that the CPU should give 80% of its time to foreground and 20% of its time to background. And that foreground is running on round robin, while background is running on first come, first serve. That's an example. So definitely, time slice will be allocated to each queue to be executed. This is a multi-level example where we have 3 levels of queues, and each queue has its own different priority. Here we have interactive queue with priority 1. We have batch queue with priority 2, and then we have students queue with priority 3. Now, what that means is that, first of all, priority 1, which are interactive processes, will first be allocated to the CPU before priority 2 processes will be allocated, and then finally, the least priority, which is the student's priority, will now be allocated to the CPU to execute. So that's how multi-level queues work. Now let's look at multi-level feedback queue. Multi-level feedback queue is another scheduling technique which has priorities. Multi-level queue has priorities. The process can move between the queues. Now remember the previous one where we talked about multi-level queue. At that level, there was no preemption, it was fixed. When the process enters a queue, it has to stay in that queue. So if it's a round robin queue, it has to run entire till the end. And that could cause us problems as starvation. But here in multi-level queue, if a process is running through a certain process, maybe running through round robin and it cannot complete in time, you can move it down to first come, first serve for it to complete earlier or complete at the end of the day. Now, so we say a process can move between the queues and aging can be implemented this way. Remember, aging is when a process stays so long and it is not being executed. So we start calculating the age, and when it gets old, see as if the process is staying too long, we now move it to another queue to implement it faster. The parameters for a multi-level feedback queue scheduler are: 1, the number of queues, how many queues are created, and what are the scheduling algorithms for each queue. So we have to look at the scheduling algorithm. Each queue has a scheduling algorithm, and each scheduling algorithm for each queue is supposed to ensure that every process is completed fairly, executed on time. The third one is the method used to determine when to upgrade a process. One could be aging. You could say when the process is getting older, then upgrade it. Or if there's an emergency, upgrade it. Then another thing is a method used to determine when to demote a process. For example, if a process is spending so much time with the CPU, it can be demoted. We have different types of processes. Remember, we have CPU-bound processes and we have I/O-bound processes. A CPU-bound process spends more time in CPU, whereas an I/O-bound process spends less time in CPU, using the CPU. So you could upgrade a process that is doing less CPU time and doing more I/O work so that you can quickly finish the process and move on to the next. But if a process is spending more time on CPU, then you can demote it and remove it from using much of the CPU time, and let it go and spend less time doing so that everybody can have access to the CPU. The method used to determine which queue the process will enter when the process needs service. That's another thing that needs to be known. All right, you can determine which queue the process will enter when the process needs service. Now let's have an example here of 3 queues. Q0 has a time quantum of 8 milliseconds for first come, first serve. Q1 has a time quantum of 16 milliseconds. So that the first one that comes has to spend, that is, they are round robin, but based on who comes first. So if you come first, you spend 8 seconds, move out, and the next one comes in, spend another 8 seconds. That's for Q0. Then for Q1, that's a time quantum of 16 milliseconds, and the first that arrives must spend 15 seconds before the next. And finally, the last one spends total first come, first serve. Now, for us to be able to ensure that no process suffers, we have to move the processes through these queues. So if a new job enters the first Q0, when it gains CPU, it receives 8 milliseconds. If the job does not finish, we move it to Q1. Q1 will give it 16 seconds. So at Q1, when the job gains CPU, it receives 16 more milliseconds. But if the job does not complete, it is preempted and moved to Q2. All right? But if the job had finished its time at Q0, then automatically it has completed its job and therefore will not need to move to the next level. So that's the thing with multi-level feedback. Multi-level feedback is looking at reducing starvation between processes. Now, here's an example of what was just explained. We have it here where we have a process entered, had a higher priority, and was given 8 milliseconds. And because it spent so much time, after 8 milliseconds could not be executed, it will now be migrated to a lower priority of priority 2, because it's spending more time doing CPU-bound jobs. And therefore, when it spends more time holding onto the CPU, it will be demoted to go into 16 milliseconds. Now, after 16 milliseconds, if it does not still finish, it will be moved again to where there is no time slice. So it can be moved, it can spend its entire time running with first come, first serve here. Though it could still be preemptible, even at priority 3. But now it has no time slot at all, so you could execute it completely to the end. So that is what we call multi-level feedback queues. Now let's look at a situation where we talk about multi-processor scheduling, because we have seen a situation where many processors can be scheduled by an operating system. A multi-processor scheduling is how an operating system decides which process runs on which CPU when a computer has more than one processor or 4. CPU scheduling becomes more complex when multiple CPUs are available. So as you get more and more microprocessors, scheduling becomes more complex. Now, when we have identical multiprocessors, or what is called homogeneous multiprocessors, the homogeneous multiprocessors have identical functionalities and they permit load sharing among them. So you can run multiple threads in parallel among those multiprocessors. We also have non-identical homogeneous multiprocessors. They are not identical in their capabilities. So load sharing has to be done much carefully. We also have what we call asymmetric multiprocessors. Now, in asymmetric multiprocessing, only one CPU runs the kernel, while others run user program. All right, so we could decide, the operating system could be designed as an asymmetric multiprocessing technology. So only one CPU runs the kernel and other runs programs. Now you have the manager and you have the worker. So one CPU schedules the other CPUs. That also has its own problems, because sometimes one CPU will be just scheduling and therefore will not really be working. So it may just be wasting time, not really doing much. And then we have the symmetric multiprocessing also. In symmetric multiprocessing, all CPUs runs kernel and user programs. They are all at the same level. There are different scheduling approaches. One is the global queue scheduling. Here, all of them share one common ready queue. All the microprocessors share one common ready queue. And then they have the local queue scheduling, where each CPU has its own ready queue. And that's the end of CPU scheduling. Now, have a good day. Please, I'd like you to share this video, and I'd like you to drop your comments on whatever idea or question that you have, and we'll respond to it. Please like, share, and comment. See you in the next video.